All right, we have section 2.2, which is on polynomial functions of higher degree. Section 2.1 focused on quadratics, which is obviously a second degree polynomial function. This is going to be 3 and higher, mostly. So polynomials are always continuous, meaning there aren't any breaks, gaps, or holes or anything like that. Let's sketch a graph of each of these functions. We can use our calculator to help us if we don't know what they look like. Negative x to the fifth. And you might find that x to the fifth looks an awful lot like x cubed. Looks very similar. If this was negative x cubed, it looks very, very similar to that. So it's just a little bit more flat in the middle. So it actually still has those 3 points that we would have used. It's just a lot flatter in the middle. Okay, x to the fourth plus 1 is the next one we're going to sketch. And again, we're going to find that this would look pretty similar to if this was x squared plus 1, just a little flatter in the middle. Still going to use these same 3 values that were transformed here. Okay. So then similarly, x plus 1 to the fourth looks pretty similar to if it was x plus 1 to the second. We're going to talk about why that is, or what is that relationship. A lot flatter in the middle. There we go. So you always have those calculators there. So don't worry about, I don't know what x to the fifth looks like. I don't know what x squared or x to the third looks like. You can always use your calculator to help you. But if you need to do things by hand or verify, you need to make sure you write those steps down that you did. So let's talk about why x to the fifth looks like x to the third, or why x to the fourth looks kind of like x squared. There's something called the leading coefficient test, which tells us that if we have an odd leading degree, so that would be 1, 3, 5, 7 as the highest degree in the polynomial, and the leading coefficient is positive, then the graph is always going to fall to the left and rise to the right. That's going to be the end behavior, which is why those graphs looked so similar. So I'm going to just make up a function here. If we had, let's see, odd and positive, so if we had 3x to the fifth plus, doesn't matter what comes after that, the end behavior is going to be down to the left and rising to the right. The arrows are really what we're paying attention to here. And if that leading coefficient is negative, but we're still odd, then it's going to be flipped. We're going to have up to the left and down to the right. Middle, I'm not paying attention to. These are just made up functions. We're just focusing right now on the arrows and where those are going. Okay. If they're evens, that would be the second degree polynomial, which we focused on in section 1, quadratics, 4, 6, 8, so on. If that is even and the leading coefficient is positive, then the graph rises in both directions. So that would be something like 2x to the fourth plus something. It's going to rise in both directions. Just paying attention to the arrows, not necessarily the middle for the leading coefficient test. And negative 3x to the sixth plus something something. So again, the arrows are going to fall to the left and to the right when that leading coefficient is negative. So let's apply that. Let's apply the leading coefficient test to a function so we can tell what the left and right-handed behavior are just by looking at that first term. On letter A, we're looking at negative x cubed, which is odd, since the 3 is odd, and negative, since that number in front is negative, which means, and if you don't necessarily memorize these pictures, these, if it's odd, you don't have to memorize which one's which. I always think about the most basic odd function, which would be just y equals x. That's odd. It's the first power. And then I think about, okay, well, if the leading coefficient's negative, negative x, what direction would that be? The left would rise, and it falls to the right. Letter B, x to the fourth, that is even with the 4, and positive since the number in front is just 1. So again, instead of memorizing those charts, I mean, feel free, you certainly can, but if I like to just think about the most basic even function that there is, which we just spent a whole section focusing on, which is the quadratics. If that is a quadratic function that has a positive number in front, that opens up in both directions. So the arrows are going to go up. It rises left and right. Even ones are nice because you know it's going to either go up both directions or down both directions. And last one, it's odd with the 5 and positive. So I think about the most basic, which is x. And since it's positive, it would be just y equals x, which I know falls to the left and rises to the right. Okay, so let's talk about zeros. All of these things, 1 through 4 here, all mean the exact same thing. You might see the different verbiage. So you might say, okay, something is a 0, find the zeros, find the solutions, find the x-intercepts. All of those mean the exact same thing. And we can always turn the 0 into a factor by doing x minus that 0. So that's also telling us the same thing. Just be aware of that. If you see those different words, it's asking for the same thing. Don't be alarmed. Okay, find all the real zeros of this function. In the section today, everything's going to be able to be done by hand. So this is going to be factorable. If I need to find zeros, then I need to set the function equal to 0. And like I said, this is factorable. Each of our terms have an x in common, so we take that out. And then I can factor the x squared minus x minus 2. Factors of -2 that add to -1 in the middle be -2 and +1. And then I solve each of those, set each factor equal to 0. I'm going to get 0, 2, and -1. So, like I said, the zeros we aren't going to be able to do by hand today because everything factors nicely. Find the zeros and the extrema. We are going to use our calculator for the extrema, but starting with the zeros, which we can do by hand. Take something out that I can factor from both of those terms. I'm going to take out -2x squared from both, which leaves me with x squared minus 1 when I factor that out. And x squared minus 1 factors, difference of squares, x plus 1, x minus 1. Hopefully these are tricks that you remember from Algebra 1 or Algebra 2. And then our three zeros are 0, -1, and 1. Now as far as the extrema goes, we're going to need to graph this. -2x to the fourth plus 2x squared. Extrema is referring to maximums and minimums. So I very clearly see what looks like a maximum. Looks like it's at 0, 4, but I don't want to just guess that. I need to actually figure it out. And my calculator has the functionality to get the exact value, which is under second to trace, and the same place we found maxes and mins last time. Max, go to the left, go to the right, enter, enter. So when you see this kind of notation, that E, that is actually scientific notation. This is -2.837 times 10 to the -4th, which is really just your calculator rounding and estimating 0. So like I eyeballed it and said that looks like 0, 4. That x value that's written here, that is 0. If you ever see that on your calculator, don't write that down. Just put 0. So our maximum is at 0, 4. Sometimes your zeros will happen more than once. If you're looking at this example we just did, where we had setting negative 2x squared equal to 0, you're going to get x equals 0 twice there. X equals 0, x equals 0. That's called multiplicity. That is a repeated 0. And if your multiplicity is odd, which most of them are because they just happen one time, like our x plus 1 and x minus 1, those zeros just happen one time, then your graph is going to cross the x-axis, whoops, at those points. So here we see that at negative 1 and positive 1, it crossed both times because the multiplicity was odd. But with 0, hold on just a second. If the multiplicity is even, then the graph is just going to touch the x-axis there, but not cross. So we'll get a couple examples like that so we know what that looks like. All right, so let's find all these real zeros. Now this one we definitely have to use our calculator for. Definitely not going to try to factor that today. So if you have something that's clearly not factorable, just use your calculator. Most of the time today they were factorable. This one is not. Okay, zoom 6, make sure our window is correct. All right, so I see 3 times where it crosses the x-axis. 1, 2, 3. All right, so I need to have my calculator do the work for me. It's in the same place as it would be for finding maxes and mins, only when I do second trace this time I'm going to look at number 2, which is to find the 0. Let's start at the far left. It says left bound. That means I need to go to the left of the 0. If I'm following the path of this function from left to right, technically the left of the first 0 would be underneath the x-axis. So I hit enter there. To go to the right, I just need to go above the x-axis. There we go. I'm not going to guess. First one is negative 1.861 when I round. Same process for the second one. Second trace, 0. Enter when I'm to the left. Enter when I'm to the right. Negative 0.254. And one more. Notice how I started all the way to the left and then just made my way right with all of the zeros, because that makes it easy when it's asking about left bound and right bound. I can just follow the path of my little flashy dot. I need to make sure I'm below the x-axis for this left bound and above the x-axis for this right bound. 2.115 when rounded. Okay. Now we're going to sketch by hand. So obviously you have a calculator, graphing calculator that you can check all of your work with, but we are going to use our algebra skills here to do as much sketching as we can with the leading coefficient test, with our factoring, and things like that. So sketch by hand. First we're going to talk about that end behavior. I'm looking at the first term. This is even and positive. So I know when I'm done with this, my end behavior is going to rise both directions. All the steps that you see me writing down here are the steps that I would expect you to show to get full credit on these questions. Now we're going to factor to find the zeros. I can take out an x cubed. And my zeros are 0 with a multiplicity of 3. I'm just going to write M3 here to indicate that multiplicity, and 4/3. So the first thing I'm going to do on the graph itself is put the zeros in. 0 and about 4/3. Now I'm going to go back to old-fashioned plug and chug. Now that I know where the zeros are, I'm going to choose my points strategically so that I choose some points to the left of the zeros, in between the zeros, and to the right of the zeros. So I'm going to choose -1. Let's do 1/2 because I'll get a couple points in between those zeros so I can see what's going on. And then we'll do 1.5 afterwards. You can pick whatever points you want. You're the one plugging them in, so feel free to choose points other than the ones I'm choosing. -1 is 7. 1/2 is about -0.3. 1 is -1, and 1.5 is at 1.7. So we plot all these points and draw a curve through them. 1/2 is at about -0.3, 1 -1, and 1.7 is about right here. Get this little dot out of the way. And I'm going to draw my curve through with that end behavior in mind. Now, if I was to graph that on my calculator to confirm, it should look relatively like that. The things that I'm looking for are correct end behavior, correct zeros, and that you tested points to left, the right, and in between the zeros. Okay, one more of those. Looking at the first term for end behavior, this is odd with the power of 3 and negative. So it's going to rise left and fall right. Next is the zeros. We're going to set this whole thing equal to 0. I can take out an x, and I'm actually going to take out a 1/2 as well because that's going to make it, there's not going to be a fraction in there then, and we're hoping that it'll factor when I take that out. Or a -1/2 x. Then that first term won't be negative. That'll be nice. If I divide out a 1/2 from 2, it becomes 4. And the 6 doubles as well. And then the 9, that just the fraction is gone from that 9. Lo and behold, that makes a very factorable form. 2x minus 3 squared. That was a perfect square trinomial. So that worked out very well. Our zeros are 0 and 3/2. And that 3/2 has a multiplicity of 2. What happens with even multiplicity? That means it's just going to touch at 1.5, but it's not going to cross. So we'll notice that when we plot points that it's not going to go through that point, it's just going to touch there. So now I'm going to make a table with points that I chose to the left of the zeros, in between the zeros, and to the right of the zeros. So I'm going to pick -1/2 to be to the left, +1/2 and 1 to be in between the zeros, and 2 to get to the right of the 0. Again, choose more points, choose different points. As long as you have the same general shape as I end up with, that's totally fine. -1/2 ends up with 4. +1/2 is -1. 1 is -1/2, and 2 is -1. So I'm going to plot those points. Looks like that. So I can see then at that 1.5, it for sure just goes up and touches that point and then turns back around. but it does not go through there. And that's because of that even multiplicity.